Now we are online, also from the digital recording point of view. Is it working? Yes, it works. Now, what I wanted to say, yeah, we continue with uh, the MOSFET. We have had learned that the MOSFET has certain properties. The last property we learned from the MOSFET was that if the voltage you apply to the drain is larger than the overdrive voltage, then the resulting potential between drain and gate is lower than the threshold voltage. This means if you, let's keep on this line, if you apply at the drain a larger voltage than the overdrive is one threshold less than the drive voltage. Then you pinch off the channel and then you assume that the current is constant because the available current is provided by the channel. Okay. How much current is the channel providing? It is provided by this equation here. So if you reach this tipping point of the equation, then you have the maximum value, and this maximum value is reached if you set in to the drain source voltage the overdrive value. And if you do this, you have exactly this equation. That means the drain current increases quadratically as a function of the gate source voltage, starting at the threshold value itself. So at the first approximation, your MOSFET is a current source or a current sink. Source is from top, sink is from bottom, but both we say they are sources. The wording is that way. But the reality tells you a different story. We said that the current is constant, but it is changed. So the constant part is taken into account by times 1, and the additional part is here plus lambda VDS. What is that for? If you have a constant value for lambda, then you have for increased drain voltages, an additional portion of a current. This additional portion of a current is given by lambda, and lambda is calculated by this equation. It is 1 divided by a technological value. It is not an applied voltage, it's a technological value, VE, times L in the denominator. L is the length of the channel, the full length of the channel. That means if you have a certain length, then the technology defines this slope. Or other way around, if you increase the length together with the width, then you get a lower slope. That means if you want to have a low slope, then either you go to reduced bias currents, and additionally, you increase the length of the transistor. So that's now a stated I just say it now, and you say, okay, it looks good. It is understandable from the mathematical point of view. It is understandable that your channel modulation parameter is proportional to 1 over the channel length. Okay, but why? Why does that happen? Why is the current increasing if the channel is modulated? Because now, don't get confused. I'm linking now one point with another point. Okay? What happens if you increase, decrease the length of a MOSFET and you are in the linear region? Again, if you decrease if you decrease the length, so the length is decreased, and a new transistor looks like this. Okay? The rest is equal. What happens? We have learned that it happens that the equation, this large equation, says something, and the simplified equation says the similar thing, and it says that beta is increased if you reduce the length. Okay, so the current value increases if you reduce the length, but we don't physically reduce the length of the transistor if we pinch off the channel. If we pinch off the channel, we decrease the channel effective length. No, not effective, sorry. The point where the channel pinches off is reduced. It's called the effective length. And this reduction in the length is normally mapped to, if assume your transistor looks like this, your current would increase. But this transistor is already pinched off. Therefore, you are in this area. And this increase in the current in the drain, through the drain, is mapped as an additional term, which is plus lambda VDS. So physically, you reduce the channel length by pinching off earlier under the gate, and this reduced channel length increases the available current, and this increased available current generates this slope. Now, why do we have a proportionality to 1 over L? Because assume your transistor is that long. If you then apply to the drain a certain voltage, you pinch off. Okay, and the change in the drain voltage, so the change in the drain voltage changes the channel length. Okay, that point we have learned. This change has a certain proportion to the full length. If now the same voltage change at the drain is applied to a transistor which is shorter, you generate the same change, but as a relation to the full length, it has a higher percentage. So the modulation, the length modulation, is given by doping concentrations, by oxide thicknesses, and the voltage you apply to the drain. And this changes the channel length. And the length modulation proportionality in relation to the full length is small if your transistor is large, and the percentage is high if the channel length is small. Therefore, you have a proportionality, anti-proportionality to 1 over L. So that's the simplistic way of explaining why the channel modulation coefficient, which increases the drain current, is a function of 1 over L. That's it. One more person is coming in. Hi, Mr. Sulak. Nice to see you. Okay, so you got it? That's very important to take this information to your engineering life. So in integrated circuits, if you want to have a current source, you design this transistor with very large length, these transistors. Okay. Now, let's talk about the figures themselves. The typical value for 1 over lambda is 18 volts. This voltage is not a measured value, it is an interpolated value. If you just interpolate the slope of these output characteristics and the intersection at zero drain current delivers us a value, and this is the value typical 18 volts. Now, what I have said, our wish to is from a transistor to be a current source. So we wish to have a very flat output characteristics. This value is for bipolar transistors in the range of 100 volt. That means, by nature, these transistors, bipolar versions, are better analog transistors. Therefore, in analog design, bipolars are favorite transistors. But as I said, the P-type bipolar is, yeah, not really useful. Okay, now let's go on to the small signal parameters. What is the small signal parameter? Small signal is we go to small signals in analog circuit designs because we apply first an operation point. One moment. One second. So your bias you set by applying, for instance, 2.4 volts at the gate. Then you get, let's say, something around 0.4 milliampere. At the same time, you apply to the drain also the bias voltage of 4 volts. Okay, now this is your operation point of the transistor. At that point, you let the transistor work, you let the current through, and then you take a look at the characteristics to manipulate a signal. That's the purpose. We want to manipulate a signal. So let's say our signal is sinusoidal applied additionally to the gate. Additionally means in addition to the bias voltage. Then you get a certain current response. to the at the transistor. This is the most important graph for an analog circuit designer. What happens if you apply a change in the gate source voltage with the drain current? This translation from voltage to current is called transconductance. So the conductance is current to voltage, and the transconductance is the current at the drain as a function of the voltage at the gate. So transconductance. So this most important graph says you sit into a certain application voltage bias point, you apply a signal, you get a response, a current response. This current response requires you in the transistor, if the transistor makes this current response, it has to make a voltage swing at its drain source potential. Because you see your output characteristics, it has a certain slope, and that means your voltage swing at the gate is translated to a voltage swing at the drain. So this is the maximum possible voltage gain of a single transistor. And this is symbolized in these two graphs with the MOSFET. Now, let's talk about values. What is the change in the signal voltage as a function of the change of the signal current as a function of the change in the signal voltage? For this purpose, we need the slope. What is a slope mathematically? The first derivative. Okay, so we have this equation. We derive this equation by VGS, and we get, forget about this, so you don't take this into account. You get, that's the overdrive voltage, V overdrive. The first derivative, the 2 gets to this area, you get 2 times to the power of -1. And this means beta times V overdrive. So the first derivative is beta times V overdrive. That means if you want to have the transconductance called GM, then you can manipulate GM by width divided by the L. The rest is a physical property you cannot manipulate. You can manipulate the width and the length, and you can set the overdrive value at the gate source voltage. Okay, so now we know at each operating point the slope. At each operating point, you set the overdrive voltage, you know the threshold voltage. So threshold plus V overdrive is the point where you are sitting in. And if you have additionally V as a V over L, then you have your bias. And at this bias, this slope is GM. That's it. If you know this, you almost understand fully the analog circuit design because the rest is a derivative of this information. So keep this in mind. Don't forget that. Everything else is of minor importance. It is important, sure, therefore I'm talking to you, but it is minor. Now let's talk about Additional parameters. One moment. Here we have the value. Okay. Now we talk about this slope. What is this slope? The first derivative of the drain current is a function of the drain source voltage. Yeah, okay. So all our operation or our bias point, uh, sorry about AP. AP is Arbeitspunkt. It's German. It's the bias point in English. I have forgotten to switch this abbreviation. So um, I just write it here down. AP R, right? Punkt is bias. So the point where your circuit does work. And this slope, if you put in here the first derivative, we get lambda times ID. Lambda times ID. Lambda times ID. What does that mean? So the slope is conductance, but we need the resistance. It's 1 over conductance. That means 1 over lambda ID is your slope in the output characteristics. In the output characteristics, VDS as a function of ID or vice versa. So your slope is a function of lambda, and lambda is a function of 1 over L. That means your slope is proportional to L. Okay, this we have learned. You make your transistor longer, your modulation has a smaller percentage of the full length, therefore it's more flat. Yeah, we have it. Again, in the equations themselves. Take into account also these values in the boxes. These values I have put there so that you can understand how these curves are plotted using Excel. Okay, so I have used again the spreadsheet I have provided you to generate all these curves. Okay, now we have that stuff and the equivalent circuit, a small signal equivalent circuit is this. So your complicated in brackets, your complicated physical setup. I just make here a screenshot. 1 second, please. I just copy this picture of the transistor and paste it here. One moment. Now here we are. So the physical device is translated into an electronic equivalent circuit, but in a certain operation area where this equivalent circuit is true if you have your operation point, your bias, somewhere in the saturation region. This is your operation point, your bias. And in the transconductance curve, that's the VGS as a function of ID. So for the transconductance, you have up to the point where you have your threshold voltage, by definition, no current. And then it increases to the square value of VGS. Okay, and here you have also your bias point. Okay, so we have a VGS bias here, and we have a VDS bias here. And all circuits are using one bias point. In analog circuit design, we are here. And for this, we have this equivalent circuit. What does that mean? If you apply, now you see small letters. What is a small letter? A small letter is delta VGS divided by delta VIID. No, no, just delta VDS. Sorry about that. And GM is delta ID as a function of delta VGS. So the delta, the small variance in the value, is defined as the equivalent small signal equivalent value. So small VGS means small signal. GM is the small signal slope of the transconductance. RDS is the small signal slope of in the operation point. So you linearize everything of the transistor in the bias point. And if you do that, you have a current source. One moment. What do we have here? We have not a constant current. We have a controlled current. And the controlled current, control voltage is VGS. And if we change VGS, we change the signal current, ID. Why? If we change VGS, we change ID. And this changed delta ID is the small ID. Okay. And this statement that you have changed your current is given as a controlled current source. Okay, and the slope in this point is taken into account by RDS. Why does this slope represent a small signal resistance? Let's make an example. If you have a signal of 1 millivolt, if your GM is 100 microampere per volt, let's assume, then your signal current is how much? Your signal current, which is flowing in this direction, is 100 microampere times 1 millivolt is 100 micro times milli is nano, you know, nanoampere. So you have 100 nanoampere signal. So if you take a look into this current, it changes with an amplitude of 100 nanoampere. And this change is translated, so this change in current is translated by the resistor in a change of the voltage. And now assume that RDS is 1 mega ohm. That's true if you are in integrated circuits. Then your VDS is 1 mega ohm times 100 nano millimicro nano, 1 Mega, 100 millivolt. Is that true? Okay, so your change in 100 nano ampere is translated in this resistor into a change of 100 millivolt. I'm not in scale for sure, but I just wanted to state how the transistor makes from one voltage a current and from a current again a second voltage. So this is the importance of understanding the equivalent circuit of a MOSFET. But the MOSFET has additional properties. These are the so-called parasitic capacitances. And these parasitic capacitances occur physically. They occur as an overlap of the metal gate to the highly doped ohmic contact area. And in between, you have silicon oxide. Silicon oxides. Now we have. Okay, so we have a plate capacitor here. We have a plate capacitor here. And this plate capacitor is the so-called drain to gate feedback capacitance. That's the Miller capacitor. We have additional capacitances. If you have here a channel, this channel has a capacitance to the bulk. Why we have a capacitance to bulk? Here we have 0 voltage, but here we have VDS. So here we have Vx. So we have a capacitance from the gate to this point through this channel. Okay? And if your channel is pinched off, then the most part is linked to the source and almost nothing is linked to the drain. So it is also bias dependent. So the electric equivalent models, the so-called SPICE models, thus take these properties into account. And in the master's course, you learned already this stuff and are using it or trying to use it. Okay, so here is the introduction. So it is overlapped in the theory, you know? Okay, all these capacitances are present, and if you then put your bulk to ground, this capacitance, this junction capacitance from source to bulk, so the source to bulk junction capacitance. What is a junction capacitance? It's the space charge capacitance of a diode. And what is the proportionality of the space charge capacitance to the voltage? It is 1 over voltage, but square root of this value. You remember? If not, just repeat it by going back to the PN junction to the appropriate page. But this one remains, this junction capacitance. Yeah, and the combination of the drain bulk and the air drain source is the drain source capacitance we have. So we add a gate source, we add a drain gate, this controlled current source. This is the main function of the transistor, and this is RDS. So by intention, I haven't written their names here. so that you can add them and say, okay, here we are sitting in, and this is the most important one. And this guy is shooting into our knees by, yeah, it's Miller effect. Miller effect in circuit design does mean it's not a device topic now. A Miller effect says if you have a voltage at the drain to the source, but you have had only a small voltage at the gate to the source, so you have a voltage gain, then this capacitance is charged discharged multiple times by the voltage gain. So this small capacitance appears to be very large at the input. So um, in my Schaltungstechnik um, lecture in German, which I have replaced by the master's course lecture for you two, Fernando and Rauscher. And the third person, yeah, Herr Friedel. Um, there we have this topic on a certain page. One moment. The Miller effect we have talked about somewhere here. So we start to talk about the Miller capacitance. I think I have introduced it somewhere else. Be patient, I will find it. Okay, that's the change in slope if we have a cascade that we have had very recently. And somewhere we have also the frequencies topics. Okay, that's the band gap. 40. You're so great. Thank you. Okay, so we have this capacitance between so-called drain, in the case it would be now a MOSFET, and gate. And this capacitance is calculated from the small signal manner. And if you apply, like in electrical engineering basic course in second semester, the mesh equations and so-called current node equations, then you end up to have the the electrical effect of this capacitance to be multiplied by the voltage gain. So if you go to the page 42 on these slides, it is free, you can just download them. Then you can reverse calculate, you can find out which steps I have made to take into account the Miller capacitance. And overall, you can say that the Miller capacitance reduces the bandwidth of the usable frequency range of this circuit because it is a low-pass filter combined with the resistances at the gate. And if you have a gate, a common gate circuit, so in bipolar transistor it's called basis, then this doesn't happen anymore because because your Miller capacitance is shorted to ground. Okay, so I wanted to give you here a hint where you can get more information on my slides themselves, but Wikipedia is also very valuable to take a look at. So, for the MOSFET, take a look on all these learning objectives checks. So I have again flipped my slides to questions randomly. So many random questions. So take them to help yourself. Well, now we go on to have a closer look to my, from the signal point of view, favorite transistor. You have to learn, and you have to know that my background, the last background is gallium nitride, power electronics. So Mr. Friede, Mr. Fernando, and Mr. Rauscher, you are highly welcome to have on gallium nitride power electronics to make your bachelor thesis together in a group called Scalable Modular Power Electronics. That's our research topic together with Mr. Schulerus. And we have additionally linked topics, you know, in our Electronics and Drives Center in Rommelsbach. There you can also participate to the Alice team. And the Alice team will make a board, making a digital audio amplifier. And this board needs a discrete implementation of the system. So Alice team is making a differential control loop to the sigma delta amplifier. And this integrated circuit system will be also made on board with discrete operational amplifiers. And this stuff you can make on printed circuit board. And Miss is Sabrina Ulmer, who is a research assistant at the Reutlingen University, together with Schulerus and me. She has prepared an environment for gallium nitride sigma delta class D amplifiers. And you can use her environment, the new topology from Alice, and make in very short time period, in very low probability of fail, a new class D amplifier. And you can analyze and optimize your results based on real PCB you have generated, but based on whole groups who are working on this system. So you participate from master's course, you participate from a PhD student, and make your bachelor thesis using all these stuff. It is very, very useful to take this also into account. But Mr. Schulerus will catch you nonetheless and will tell you the same story. So I apologize, I was too early. Okay, so come back to the bipolar transistor. What is a bipolar? It has two poles. So if you have a NPN transistor. Uh, this is the sum of diodes from the first point of view. Okay, you can also change PNP. So that's also a bipolar transistor. So first take a look how it is made. You make these two diodes antiparallel, NP, and then here N. And you see here the the index plus, 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 and minus. This means the emitter is highly doped. The base is lower doped, and the collector has the lowest doping concentration. Why? We will learn. We have now an N P N transistor. This NPN transistor is this area. So here we are sitting in, if we talk about a transistor. But to have an operational transistor, you have to operate it. You have to contact it. And if you want to contact it, let's assume you have such a transistor, okay? So a typical transistor you can take into your hands. Um, you have your base, emitter, collector pins. And usually in power electronics, your collector is sitting here, and therefore your collector is the backside. Your collector is here, this pin. And I think usually the base is at the right hand side and the emitter is at the other side. Okay, to be able to contact them, you have to have a contact area with the base metallization, the ohmic contact. The emitter is placed just in the center of the transistor, and then the collector is placed here. So what do we have additionally to the intrinsic transistor? We have a base resistance to the channel. The channel is distributed. The base area is distributed. So you have different resistances on a different location in the base. Okay, we have here also a resistance of the emitter. And we have also here a resistance to the collector. So we don't take into account all these parasitic resistances and say transistor. And let's talk about this transistor. And therefore, we can say emitter here, N-type, P-type, a symbolic contact to the P-type, and N-type, a symbolic contact to the N-type. Therefore, we talk about these box-shaped doping areas. And the symbol to these transistor are placed on top and within the very basic circuit diagram. So you control your transistor between base and emitter, base emitter voltage, and you apply also a collector emitter voltage, and then you have your very first circuit diagram here. And the PNP, yeah, if you take into account the emitter here, there you have the emitter here. If you take into account the base here, and for the PNP, the base is here. So the base emitter voltage is here. And like in the MOSFET, if you change just the index variables, you have the correct biasing polarization. So VBE is positive. VEB is positive for the PNP transistor. Okay, and the collector is at the lower potential. So usually you draw a circuit in the stack of the potentials. So for the usually used NPN, this is the powerful one. The emitter has the lowest potential, the collector has the highest potential. And for the PNP, which is the weak transistor, very weak transistor, the emitter has the highest potential and the collector has the lowest potential. Therefore, it's flipped upside down. Okay, now let's talk about its way of working. Because if you take here a closer look, if you apply here a positive voltage, and here you have your ground. So let's take here the value. If you apply 10 volts, and here 0 volt, then you have here your N type, here you have your P type, you have an PN junction here. Somebody tries to enter my door. No, I don't have to go. That was a delivery service. They placed a parcel at the door. Sorry. So you have at the N type, a higher voltage compared to the P type. So this diode is reverse polarized. Okay, now let's polarize it a little bit different. Let's say 0.6 volt. So the P type towards the emitter, it's the N type. It is forward polarized. Okay, here a current is flowing, but from collector towards base, we have a reverse polarized diode. So you can't have a current here through if you have just two diodes. But nonetheless, it works. Why? Because we have the majorities, the N-type. These majorities, okay, first we have zero bias, and at 5 volts at the collector, if we have here a 0 voltage, if we have here 5 volts, then we have the so-called extended space charge region, because this diode is reverse polarized. In the first approximation, this current is 0, and due to no bias, the base current is also 0. All currents are 0. And the equivalent circuit of this type of transistor is switched off. That's understandable. No current because of reverse biased collector base diode. But now you can have a current. We will talk about in more detail in the following slides. One moment. Yes. If you apply a forward voltage between the base and the emitter, then you have a certain current flows. Assume here this is a diode. It is a diode, sure, but it is only a diode. Then the majorities are injected to the N region. The majorities are injected into the P region. And here they recombine. Here they recombine and make current. So if you take a transistor, apply to the base, emitter, a voltage, you have a PN diode. Nothing special. For this, please go back to the slide 59. There we have our PN diode. You inject the holes, the electrons, they recombine and make current. We have learned that. But for the bipolar transistor, we have more. We inject the electrons into the base, but we don't give them the chance to recombine. We prevent the recombination. That's the way the bipolar transistor works. although you have two diodes antiparallel. So the recombination prevention gives the chance for the electrons to pass the base and be sucked up by the collector, which collects the electrons, therefore the name. And this current, which goes through, is no more zero. The current into the emitter, so because of the definition, it is smaller than zero, is almost equal to the current. Oh, is my pencil now has no battery anymore? Yeah, my pencil has zero voltage. Okay, 1 second. Does my finger work? I just switch off my pencil. Oh, okay. I'm just telling you what I'm doing by the mouse. Do you see my mouse? Okay, great. The current into the collector is the same, almost the same like the current through the emitter. And as they are all defined towards the terminals, the one is larger than zero and the other one is smaller than zero. That's definition. So you have a small base current. Okay, why we have a small base current? Because you inject the holes into the emitter, and this current defines the base current. You inject the electrons from the emitter into the base. This defines almost the complete current through the transistor. Now let's take a closer look at the space charges and the conditions within the transistor. If you apply a forward bias, it's a PNP transistor. You see? A PNP transistor. A forward biased PN diode has a certain space charge, and this space charge makes you this lowered barrier for the holes to be injected into the width and the base. So the base area has a certain width, and this area is neutral. Now, the wording is now changed. This width is in the direction of the flow of the charges. So if you're okay, one moment. I have to increase. If you inject your holes from the base, from the emitter to the base, all your flow of your holes here are in a neutral area. Why you call it neutral? Because, now I have to shrink again, because your injected holes into the N-type are minorities. So the bipolar transistor is a minority carrier device, like the PN diode. These minorities are accumulated here and diffuse through the base. What we have learned at the space charge boundary of a diode which is reverse biased. Let's go back to this condition. We learned that a diode, if it is reverse biased at the space charge boundary, all minorities or all carriers who get into this electric field are transported through the electric field. And this wording I have first applied at this diagram on page 52. There, I said, if you apply a reverse bias, you first increase the space charge. Okay, the charges in the space compensate for the applied voltage. Okay, we learned that. And the minorities at the edge of the space charge are drifting through the space charge and making the so-called saturation current. Now, now the bipolar transistor is making the same gain, but with increased number of these carriers. The holes are injected into the base. This base width is neutral. This accumulation is drifting through and diffusing through the base. And at this boundary, your concentration is zero because of the reverse biased diode. So all holes which are coming here by diffusion are going through this space charge and are collected by the collector. Okay, now why are these holes coming here are reaching this boundary? Because of this picture. If you have okay. These arrows look different compared to these arrows. And if you zoom out, it is just a image compression error. Sorry about that. So the PN diode, so the PN diode is forward biased. So you have the flow lines. The holes are coming into the base. You have an NP diode. It is reverse biased. The space charge is increased. And what is flowing here? What we have learned, the minorities at the space charge boundary are flowing through the space charge. And how these minorities are generated? They are generated thermally. Therefore, this generation of electron-hole pairs, and these electron-hole pairs are separated and make current, but a small current, your reverse current. So what we do now, we take these two diodes, leave away the contact of the N of the base, and connect these two diodes directly together and place the base contact here. What happens? Nothing special. Your flow lines, the holes come in here. From the base, the electrons come in here and recombine, and you have a classical p-n diode. The thermally generated minority carriers are separated and make a saturation current in the reverse bias diode, and nothing special happens. What you want is, what is your aim? Your aim is that these recombinations here does not take place. And this means, I think my pencil has now enough charge for the next 15-20 minutes. Let's test. Okay. If you now reduce the space charge boundary distance so that this recombination doesn't take place. So physically, you place the second space charge to here so that the probability of recombination is almost zero. Then you have this constellation. All holes go through. Perhaps one is recombining and makes your current, which is available, less for the collector. So you assume here a big arrow, 1 second, a big arrow, and then a small portion is recombined due to the base current. This base current you cannot avoid, but if you reduce the N doping compared to the P doping, then you reduce this number of electrons which can be injected to the other side. Therefore, the base is doped lower than the emitter is doped with a different time, the opposite type. Okay, now you have a smaller arrow, and from this portion, you have a certain percentage of recombination, almost no one. So the most current goes through the base, through the space charge region, to the collector contact. That's the way of working of a bipolar transistor. Now the names. The physical length of the base is this one. The neutral width is this one. And the neutral width is the physical length minus the space charge distance from 0 towards base. From this point towards the base. Okay, now we have the flow line explanation of a bipolar transistor. Let's go over to some words about the variables with which we want to calculate. Now it is getting very tough. Now we want to calculate the base current, the collector current and the emitter current. What can we do? First, we gave them all the appropriate names. How? We learned from the PN diet that at the contact we have the full hole current. We learned that a portion of this current is at the space charge boundary, is carried by holes. The other portion is carried by electrons. Remember page number 60. There we said at the contact everything is whole. 1 second. Yes, everything is whole current. At the space charge boundary, we calculated the minority carrier concentration. At the space charge boundary, we calculated the minority carrier concentration, and we assumed that this minority carrier concentration is equal at the other side because of the space charge is very small, the space charge width. And then we know now this and this current. So these currents we know. So therefore we were able to calculate the full diode current. Don't forget that, although it is long time ago. Okay, now we are here. Okay, so we have this portion and this portion. Let's go on. We assume that here we have the same, like at the PN diode. Now, let's go to this boundary. And at this boundary, we have a slightly different hole current here compared to here because of this recombination. But we assume that this width is so small that this change is negligible. This is assumed. So we assume that this one is equal to this one. We assume it by physical shortness of this area. Okay, and the collector current is the sum of this whole current and this electron current, like in the p-n diode, but in the reverse polarity. So we learned everything about all these current values, but we don't know the absolute figures. But we start about with just naming these guys. And using these names, we just name additional things like emitter efficiency. What is an emitter efficiency? The efficiency of the emitter. Sorry. The emitter efficiency is how much whole current you get by pushing current into the emitter. So this relation of these currents is the efficiency of the emitter. And you know by the PN diode that this length is defined by the n-type doping because this number of flow lines is proportional to your doping concentration. This means your emitter is efficient if you dope the base lower than you dope your emitter. First indicator, just as a qualitative statement. Let's go on. Our base transport factor, what does that mean? You have a certain number of holes which appear in the base, and which portion of this number of holes or flow lines does reach the collector? You have a certain recombination. That means the base transport factor is assumed to be 1 by physical dimensions defined in the manufacturing process. So what portion is reaching the collector? Hopefully the same portion. Now, by looking at these variables, what is your collector current? It is the survival part of the holes coming from the emitter, going through the transistor, plus the reverse current of this diode. And this is given here. It is by the flow direction definitions, you have all these minus signs. Don't be confused. It is the sum of this current and this current. That's it. Additional stuff about the bipolar transistor. What is the gain in the current if your transistor is in the common base configuration? What is the common base configuration? Your base is at the reference potential. And what is your current gain? Your current gain is has the definition, this one, referred to this one. And this is almost 1. Okay. And in the in analog circuits, we use very often the common emitter configuration. And there, if the emitter is a reference voltage, you control the base and get a collector current. If you control the base, you put in a base current. And this base current produces a collector current. So a small base current produces a large collector current. And this is calculated by this equation. It's the current amplification. Don't be confused. It's also called beta. It has the same variable like the transconductance parameter in the MOSFET. But here it does mean the current gain. Sorry about that. It has happened to be equal. Now, let's try to understand how these currents, this one, this one, this one, is happening. Let's assume we have only a P-N diode. Then, in a forward bias condition, you inject the electrons to the P area, you generate your delta N. You remember? Do you know that? So this is your injected additional charge carrier concentration. And this carrier concentration relaxes as a function of the location. We learned that in the range of page 59. Okay, so from the p-type, you inject the holes into the n area and generate also, sorry, you generate also an additional delta p here. But this concentration relaxes also towards P and P0 in the N area. But this diffusion length, you remember the diffusion length? How large was the diffusion length? Let's go to Windows. Please open the spreadsheet. Windows, Bildschirminhalt, Fenster. I'm looking for the appropriate window name. Here we are. We learned that the diffusion length in the PN diode is let's go here. Here we are. I'm just waiting for the diagram to happen. Yeah, here we have not visible the space charge thickness and the scale Here at the lower part is, one moment, I'm waiting for the figures to appear. Now we have our scale is in the micrometer range, the space charge region is in the nanometer range, and the diffusion length was the tangent or at the slope at the space charge boundary. And so if you think about this tangent, you have let's go back to the slides. Go back to slide 61, please, or a little bit before. Let's go to slide 57. Here we learned that our concentration disturbance is relaxed to 1 over E at a certain distance, at the distance of the diffusion length. And these values are in the micrometer range. You can let calculate in the spreadsheet. Now I come back to the bipolar transistor itself. You understand how this stuff is linked into each other. So therefore, you should have usually a wall of slides, and we should stand in front of this wall and pick the appropriate information together. Now I try it out, nonetheless, by the way of this lecture. Okay, so if this distance is in the nanometer range, and if this relaxation distance is in the micrometer range, now comes a combination with and. And this distance at that point, the concentration is zero. Why? Because you reverse polarize this diode. Then you can assume the following thing. What is this curve if you put this point down to zero? You can say the concentration here, the concentration there, and in between we have a straight line. Therefore, you can say your concentration of the holes is reduced anti-proportional to the location towards zero. That's it. And also the concentration for the minorities in this P region is also zero because of the reverse polarity, like here. Now we have at every location first, the concentration. Second, what we wanted to know to calculate the current, the concentration and the slope. Why slope? Remember the flow rate. The flow rate was even before. Do you remember the flow rate? Concentration here, concentration there. The diffusion constant and the delta concentration gives the flow. And this flow gives us the current. And this we do now again. What is the current flow? It is the slope. What is the current flow here? It is the slope. What is the current flow here? It is the slope. What is the current flow here? It is the slope. And this statement we can make by first setting the equation of this shape we have learned at the bipolar transistor. And what is this shape? It is a straight line equation. You know, at 1, and then you reduce the value as a function of x. Okay, and we start at the maximum value and we go down with x. We have it here. And this slope and this curve shape we have here. Everything we have learned from the analysis of the p-n junction. Now, let's take the first derivative of them. One moment. N, P, N, and we know the equations here. How we get the current? We get the current by the first derivative, like in the PN diet. So if we take this equation, we get this part. So let's put together some Lego puzzle parts, okay? So from the first derivative of the concentration, we got this current. From the first derivative of this concentration, we get this current. And this is almost equal to this current. For the electrons, we have had this slope. So the first derivative here, we get the current. The first derivative here, we get again the current. And if we do this, we get these equations. So we don't have to calculate it. We just have to know how we get it. So my question can be to you in the examination, how we do the calculations of the fucking current values at these points. It can be then the answer, okay, what is current? The change of concentration. And the change of concentration times area times charge is the current. So the change of concentration times area times charge, elementary charge, is the current at that specific point. That's it. And now let's calculate the emitter current, let's calculate the collector current, let's calculate the base current. Because we know all the individual puzzle parts, we put them just together. And if we do that, we get, so I have simplified that stuff by putting some constants outside the equation. So some constants are put outside the equation, outside the exponential equation, and all stuff we have is we have an exponential dependence to the control voltage, also for the base. So that's the way of calculating the transistor current in the case, now, in the case V emitter, that's a PNP diode, V collector emitter, the emitter collector in this case, emitter collector, and minus E collector. And this curve looks like this, but we have calculated these currents only in this area because we have a reverse biased collector base voltage. It is reverse biased, and we have a forward biased control diode. And this is the definition of the placement of your bias point. So these equations are valid for a bias point in the active forward region. Okay, I think that's more than enough for this morning session or before afternoon session. Let's take a big break. What do you think? Up to 2:15, so that we have enough time to cook something and so on. So I would like to continue after 14:15. Is this okay for you? Thank you very much. See you later.